All right, so at this point, I believe anyone learning in this lesson is ready to look at some further examples where I formally introduce the steps and standardize the work, the kind of work. So this next couple examples, this next few examples I'm about to show, they aim at this particular skill where you're gonna just simply look at the description of the either a population growth, a natural growth, or a natural decay, and be able to derive the exponential function that models the growth like that. And in each problem, we are going to give two different versions, two different models, a continuous model function and a periodic model like that, assuming that you have learned all of that detail about what a continuous model is and what a periodic model is. Okay, so now let's look at our example 3. All right, so now just for you to know, we're in example 3, but I am going to head over to my computer station and bring up the actual the worded description on the computer screen like that. Okay. All right, so now here we go. Let's read the worded description of our example 3 right here. So now at the beginning we have, so for the beginning the description, all we have as far as the information is, we have a trash dumpster that starts with 5 pounds of garbage. That's all there is. A trash dumpster that starts with 5 pounds of garbage. And now in this beginning, the information of the example, it's asking us to write a function which represents the amount of garbage in the dumpsters after t days. Okay, the amount of garbage in the dumpsters after t days. All right, so no question has been introduced yet. So later on throughout the question, I'm going to call it, on each of the questions, I'm going to call that part A, part B, and part C, and so on, etc. and etc. Okay, but the idea now is that think about the amount of garbage that's being dumped into the dumpster right there. It's a quantity, and it can grow because there are people keep dumping their waste in there, putting their garbage in that dumpsters. And so now, surprisingly, shockingly, the amount of the garbage in a dumpsters can also be modeled by an exponential function. Okay, or maybe I revealed this a little too soon right there, but let's head into the actual first question. All right, and so now we want to model the amount of garbage in t days. And so now it kind of reveals already that the default time period here is in days right there, is in days. So 1 day is 1 default time period, but it will get even more further clear once we get to the actual question. All right, so now here we go. Let's look at question part A right there. All right, so part A of the example. So now you can see that, you see when this statement right here, write a function which represents the amount of garbage in the dumpsters after t days. This statement was not completed because now there's the requirement. So part A really is just to bring in, so mainly in this problem, in this entire example, every question is a continuation of this statement. We want to write a function. But now in situation of part A right here, if the amount of garbage increases by 3% per day, if the amount of garbage increases by 3% per day. All right, and so now if we put all of that information together, let's extract out a few things right here. All right, so it looks to me evidently that this 5 pounds right here is the initial amount. Okay, a trash dumpster starts with 5 pounds, and that's how I know this 5 pounds right here is the initial amount of garbage. All right. And so now let's go ahead and write down the information we have. So we can call the amount here or the quantity here, whichever variable's name we would like to. But here it's just me, I tend to call that Q. So now Q of T is the amount, okay, the amount of garbage in T days. And that's what the t variable is for. So t is a time variable, but I'll get to that even more detail later on. But so now the initial amount. So the initial amount is seen, is caught right from the wording description quite clearly. So the initial amount is 5 pounds. All right, 5 pounds. All right, so this is indeed, now once we name our quantity as a function q of time right there, of the t variable, then this is also the same as a label over here. This is q sub 0 right here, equal 5. All right, q sub 0 equal 5. All right, and so now let's get back to the computer station right there. Let's get back on the worded instruction on the computer screen and extract out further information. All right, so here we go. So now we want to write a function which represents the amount of garbage in the dumpsters after t days. And so that is the reason why I already set up that function q of t right there that we are going to find. But now the situation in part A is that we want to find a function where the amount of garbage increases by 3% per day. So increases, okay, and then 3% per day. 3% per day. So these two pieces of highlights right here are indicating that, first of all, our amount of garbage is a growth. Okay, and now that rate right there, that constant rate given right there is indicating clearly that eventually we're going to lead into an exponential model, an exponential function model right there to model our garbage amount. And that's how earlier when I was introducing the problem, when I was just reading the beginning description before getting into the question, I said it a little bit. I said it a little bit that it would be an exponential function. And now it becomes clear and evidently because of this information right here. The amount is increasing by a fixed, a constant percent increase in each of the default time period. All right. And so now let's write it down. So we know it's a growth. And so this 3% right here is indeed referred to as the growth rate, okay? Because we know that it's growing, the amount of garbage is increasing, it's growing. So now we have a growth rate being 3%, but 3% here is per day, okay? 3% per day. Or we can write that as a 0.03. Okay, per day. I mean, eventually into the actual calculation, we're going to use the decimal right there. All right, but now we are just about ready to tackle down the problem. At this point, allow me to bring in two choices. So once again, we have learned prior to getting into this example over here. Then on one hand, we can use the question did not tell us. We have to decide. Okay, so now just about two different choices. Which one is the proper choice for our situation right now? I'm trying to show anyone learning in this lesson that the thought process right there. So on one hand, we want to go with the model where it's initial amount times 1 plus the growth rate, and we can notate this as R right here. This is our R right there. Growth rate here is R. So on one hand, we're going with Q of t equals Q sub 0 times 1 plus R to the t. And again, and of course, just like what I was explaining before we got into the example, then the process itself is already a continuous process. Okay? Even though the model here, we call that it's a periodic model. It's just a name indicating that we're using. So right now we can see that it's just generally written that it's growth rates, okay, and the model that I write down right here is called the periodic growth. The growth model for here, okay. But the process itself is already a continuous process. Because people, again, think about that dumpsters. People don't really have to wait until tomorrow to come back down and dump more garbages in there, okay. Because maybe it could be a dumpster at a crowded public place, so there's no security, there's no one that force people to only come in and drop the garbage at a certain time. I mean, if that scenario happened, then it's going to be a different kind of problem with more complexity. But here we're just going to assume that, hey, anyone at any time of the day can stop by and dump garbage there. And that's the reason why this is a continuous model. It's going to grow continuously. It's a process that's growing continuously. So what matters for us is, so the periodic growth model is just simply a form. Whether we're using a base like this in the form of 1 plus or we're going to use the base in the form of Q of t equals Q sub 0, the initial quantity, but in base e raised to the k t power. We have to make a choice between these, and which among the two choices right now at this particular problem, for this particular problem, part A is the most suitable one, or being the most direct one. I'm not saying that once we made our choice right there, then we cannot go with the other choice, but among the two choices here, according to the given information, one choice will be more direct than the other one. And that's the point right there. So let's head out for the more direct one, the closest one to reach, and then we will see what we can do after we come up with the one that's most suitable. Okay, so the two choices here. Let's decide. And that's the reason why now, if we're looking back at the rate right here, right in the description, see all it said there is a growth rate. Okay, there was no continuous word attached to that rate right there. And I can convince you by looking back at the reading, the worded description right here. If the amount of garbage increases by 3% per day, everything I highlight is simply just indicating, or generally just indicating 3% per day. But no detailed terms about being continuous or being a relative rate. And so that means this is just some general periodic rate out there, just any general periodic rate out there, which happens more commonly. Okay, and so now in that way, now we have a direct clue. The rate itself right there gives us the impression that it's just a general rate, a general growth rate, periodic rate. Okay, because again, in the way how I was explaining, there was no detailed word saying continuous, okay, or relative rate. There was nothing indicated like that. Nothing indicated that the rate given here is a continuous rate or relative rate, according to Professor James Stewart, according to his way of wording it. And so that's why here we can just simply regard to this rate here as a some general or generic periodic rate. And that's why among the two models here, this is the more direct one. This is the better suitable one right here. Whereas here, this is because this model here, see, base E, and this is what we call continuous growth model. So I'm not saying that from this information we cannot get to that, but it takes longer routes to get from this information to that. That's why this one here is a lot more direct right here, because R is already given immediately. R equals 0.03 already. Whereas here it's base E, it's not directly given yet. That's the idea. All right, and so now once we have been clear about which model that we're gonna head out for, here we're gonna have to go with more directly we're gonna head out for, in this particular situation, the more direct model is the periodic growth model over here. All right, so now R is 0.3, okay, and raised to the t, so it comes out as easy as Q of t equals, this Q sub 0 is my initial amount, 5 pounds in the beginning. So now it's 5 times, so according to the general setup that we have already learned prior to getting to this example, then it's going to be 1 plus 0.03 to the t. It's simply just that, just pound right into that given that formula being indicated. And this is already a perfectly fine looking periodic growth model right there. It's a growth, exponential of course at this point of your learning. And then we're using just some general periodic growth rate. And that's the reason why people call this the periodic growth model right there. Even though again the process itself is well continuous. Okay, and so now in this way right here, we can rewrite this as 5 times base 1.03 to the t. That's our function right there. All right, so q equals 5 times 1.03 to the t. We are done with this. So it took me some explanation because I just want to ensure the proper understanding of and the solid understanding of my students. But it should take just that little amount of time. All right, and so now that's all for part A right here of this example 3. We are now just done with example 3. So this is really part A. Okay, and so now let's head out to part B of the example. I'm going to now navigate out over to the other board, and I'm going to pop in that computer screen right there to show part B of the example. All right, and so now same problem, but now you are put in a different scenario. Okay, so a trash dumpster starts with 5 pounds. Okay, we know that, so this is our initial amount, 5 pounds of garbage at start, and we want to write a function which represents the amount of garbage in the dumpsters after t days if the amount of garbage increases. So now, unlike part A right here, here there's a rate, but this rate here is indicating it increases continuously by 3% per day. Okay, it happens to be the same, the number 3% like part A right there, but now if we're looking at a little more closely, it's indicated clearly that this is a continuous rate right here. Okay, so it's still an increasing quantity, it's still a growth problem, an exponential growth problem in part B right here, the situation. And of course the process itself is a continuous process, but now this rate here is a continuous rate. All right, so now on my left board here, all right, so this is part B. We're still in example 3. Yes, Q of t is the amount. And of course, the two problems here in part A and part B are meant to be independent from each other. It draws the beginning information that there's an initial quantity. But in the end, think about these are two separate situations like that. And because I purposely want to, after this example, I purposely want you to learn that skill, how you can construct your own exponential function by getting yourself routinely click into those different terms like that leads yourself into the correct model, correct form of your exponential function. Okay, so right now Q is the quantity or the amount in t days right here. All right, so the amount of garbage in t days. All right, and then now with this part B right here, yes, we have the same initial amount. So the initial amount we're looking at is 5 pounds. All right, but that means this is Q of 0, because this is when time equals 0. Then we're looking at 5 pounds. So let's use the notation Q sub 0. So I'm looking at Q sub 0 equal 5. That's the initial amount. Okay, and so now we still have a growth rate. We still have a growth rate, and I know it's a growth rate because the problem was saying it's increasing, the amount of garbage increases. So it's a growth rate by 3% per day. And I could have also mentioned this when I was going over part A, but this makes it clear, this clarifies that, you know, our default time period is in days right there. Okay, each day is one default time period. But at this point, when we're working with these natural the growth or decay processes, it's all continuous, so it shouldn't be too important about the default right here. But now this is what, for this particular problem right here. So we've had almost everything we need. And yes, this rate right here in decimal is a 0.03 per day in decimals. It grows by 0.03, increases by 0.03 per day. But here's the thing. So just like the previous problem, in our thought process, we are facing that decision line right there. We are facing that decision-making line right there. That are we going to use this model over here? Q of t equals q sub 0 times 1 plus r to the t. Or are we using q of t equal q sub 0, the initial amount, times base e raised to the kt power, where this k here is called the continuous growth rate. Which one is the more suitable one in this particular situation? All right, and so now needless for me to say, anyone viewing this lesson already have had something in mind right here. I will go with this version right here. I will go with this particular model because so here's the thing. I did not write it down yet, but in the problem itself, there was this word that clicked into my attention, that got into my attention continuously by 3% per day. The amount of garbage increases continuously, and that word right here is printed in bold face right here. Okay, so continuously by 3% per day. So again, if you are working with some problem that's given in the textbook written by Professor James Stewart, then this term may be written as relatively. Okay, increases relatively by 3% per day. It means the same thing as continuously as written here. All right, and so now I'm gonna put that information a little more as further detail here, and the more detail the better it gets. All right, so that this growth rate is not just any. This growth rate right here is not just any general growth rate out there, but it's a continuous growth rate. All right, so it's making the story so clear at this point. Continuous growth rate. And now we are so clear that we are going to head out for this model over here, because this model is directly attached to this. This is not our R value, but indeed this is our K value right here. Okay, this is not our R, nope, this is our K value. That's what it is. And so that's why, since having K so ready already, so why not heading out for this model instead of using that? And I'm not saying that from this information we cannot get to that the other model, but this getting here will be a shorter path. All right, that's how it works, and that's how we put our thoughts together right there, and it's the thought process that I was giving out earlier. All right, but so much explanation. Now we have a firm decision. We're going to head out for that model right there in particular, if we're in that situation where we are deciding. So now I'm going to put this away, and then I'm going to make some space for writing down some more work right here. All right, so now you're going to even see things are so ready for us already. So with our function, tentatively to be q sub 0 times e to the k t. So now note that this is our k value. Well, now let me note directly in here. This equals our k value. All right, and so now I am going to have the following. Q of t equals, this q sub 0 is our initial amount. It started out whatever day that was, 5 pounds. 5 pounds, but I'm going to multiply with base e to the 0.03 because it's k, 0.03. It's a positive rate right there. And then 2 times 0.03 t. This is surprisingly our ending point right here for this problem. We're done. Okay, so this is, and we call this the continuous growth model. Okay, I did not make this final label on part A earlier, but here allow me to emphasize this. All right, so continuous. This is continuous growth model. Okay, so it's a model here. It's a function in the purpose to model, to predict the future value of our garbage amount like that. Okay, but then it's this way of how we're writing it. It's a continuous model. Okay, it's a continuous model. So base e is associated with continuous model, and the value k right here has to be the relative growth rate, or we have to have that clear indication, the relative growth rate or continuous growth rate. Other than that, if it's written into some general growth rate right there without the word continuous or relative, we start out easier. It will be started out easier with the periodic growth rate right there. All right. All right, and so a little bit more before I leave this example right here. But so, as I said earlier, even though we chose this periodic growth rate right here, okay, and I'm not saying that the two functions here are the same. They have different. I mean, the process is the same, but you know, the way how this indicated here already lead into different functions. So, if the problem is simply just written like this for you, and you came up with the easier, I mean, with the more direct model being the periodic model, then and it was not asked in the question, but what would be or what will be out of this form right here? What will be the equivalent? What will be the equivalent the continuous model right here? Because right now we are clear that this is the periodic model. Okay, this is the periodic growth model. Okay, that's the periodic growth model right there, simply because the rate did not come with the word continuous or relative. But then because of that, if we think about getting the continuous growth model, it is entirely possible and doable. But once we're done, it's not going to be the same as the one that we saw in part B, because you see the meaning. That's why having a clear indication is extremely important. If it's a 3%, but without the indication that it's a continuous model or a continuous rate, then it comes out with this. And now if we want to convert this, if we want to change this to continuous model, here's how we're doing it. Okay, so now allow me to erase some extra space here. All right, so just focus right here. We have learned already that just right before getting into this formal example, that 1 plus the periodic growth rate right here must equal e to the relative growth rate. If we would like to go with this form right here, then again, we have this fundamental relationship between periodic growth rate and that continuous growth rate. And so for that reason, now 1 plus r is clearly this 1.03 in our particular problem. 1 plus r because that was 1 plus 0.03. This is our r. 1 plus r equals e to the k, which leads to 1.03 must equal e to the k. And again, this is just extra. Okay, this was not asked in the actual problem itself, but I would like to just point it out. And so now, if we want to go to if we want to find the k, now have a closer look at our equation again. It's an equation that is in exponential form. And so we have learned in some lesson before this particular lecture about anytime we're having an equation in exponential form, we can rewrite that in logarithmic form. And that's how, anytime we're working with an application of an exponential function, then at least 20% of time in one problem, 20% of time, there will be 20% of one problem, actually not 20% of time, but 20% in each problem has to be dealing with some logarithm problems. Okay, so logarithm will be involved in about 20% of pretty much any exponential application problems. All right, and so now with this one right here, I see that e to the k equals 1.03, and in our role we want to find out what k equals to. And so in that way, easily I can write k equals natural log of 1.03. K equals natural log of 1.03. Okay, and natural log of 1.03. And that's how I see we have to understand how to operate with log right here. This is a place where once again we enforce our understanding, we apply our understanding of logarithm in these problems. All right, and so it's a friendly it's a friendly warning for anyone. Okay, it's a friendly something to let anyone know that there will always be about 20% of 20% in each problem in each problem about the exponential function application. We will have to work with logarithms. Okay, there will be about 20%. On any problem applying exponential function, we will have a logarithm problem. Okay, in each of the exponential application problems. So now I'm going to head over to the calculator. I'm going to head over to the calculator and pull out that particular problem, that particular value for that. All right, so now on my calculator, I'm going to go ln 1.03. All right, and this will be my value right here. So this is now going to be my continuous rate. All right, my continuous growth rate. And let's round that to 5 decimals here. And so in that way, I am now ready. So allow me to erase all this. So natural log of 1.03, according to the calculation we've had earlier, it's 0.02956 if we're rounding to 5 decimals. So now we are ready. Even though it was not asked for, we can still find, see, we can still find the continuous growth model as following. Q of t equals, so this is 5 times e raised to the power 0.02956 t. That is our continuous growth model, even though it was not part of the problem here. Okay. All right. And so what about part B of the example? Continuous growth model was the one that was more direct. So we got that one first. And so in the way how I'm seeing this, see, if the problem has given us just any general periodic rates, then the periodic growth model would be the ones that more direct. So naturally people would pull this out first. And then if you would like to, and if you need to bring your model into a continuous growth model right there, then you have just seen the math earlier. Okay, so I did that extra work even though it was not asked in the problem. And so now on this board right here, again, we have already arrived at the continuous growth model. But what about so from this continuous growth model, can we still find the periodic rate or the periodic growth model out of this? Okay, and again, don't get me wrong about the periodic growth model, meaning the process will be only happening periodically. Nope, the process will be always a continuous process like that. It's just the way we represent the modeling function is based on the periodic rate. That's the idea right there. All right, or we're just trying to go away. We're trying to go away from base E. So now, yes, I know this is the continuous growth model, but so from that understanding again, 1 plus r, the periodic growth rate, plus 1 must always equals e to the k. We have found our k to be 0.03 previously, right from this problem. Okay, so that means now directly in this problem, I'm looking at 1 plus r equals e to the 0.03. That's simply just that. Okay, and now, right from that problem right here, I'm simply just going to, because in the end, and this is not even an exponential equation anymore. We have a variable to solve, I admit, but e to the 0.03 is simply just a value, a constant. And now solving for the value of r right here, I'm just simply going to subtract 1 from both sides. So I'm going to end up with r equals e to the 0.03 minus 1. And this will give us our the periodic growth value right there. Okay, and as a matter of fact, we don't even have to do this, because the point now is, even if we get this r value right here, we're still going to use that in the form of a 1 plus r. A 1 plus r. So truly speaking, that was all of that steps of mine was really just too much. Just 1 plus r equals e to the 0.03. 1 plus r equals e to the 0.03, because our actual base of the periodic the growth model is the base 1 plus R, not base R. All right, anyone at this example, you must have seen enough cases throughout my demonstration problems prior getting into this. So now really for a periodic model, we only need to get to that point where we're calculating e to the k, get that actual value, and that value will equal 1 plus R, and this is our final destination already. All right, so let's go ahead and get the work done right here. So now on my calculator, e to the 0.03. I'll just simply punch it in, and this is the value right here. So this is also known as my 1 plus R. So R is indeed my periodic rate. Periodic growth rate is 0.0304554534. But now 1 plus R is this entire value right here. All right, so I'm now ready to finalize my function. So what I'm looking at now is for the periodic growth model, I'm looking at Q of t equals 5 times 1 point, and let's go with 5 decimal places. Okay, 1.03045, okay, to the t. And this is the periodic growth model right here. So that's why now, so I was yelling this out earlier, but it's, see, the two problems in part A and part B are completely two separate problems. They don't come to functions that are equal. Now these two functions are equal because they are in the same problem. One of them is in the exponential growth model expression. One of them is in the periodic growth model. Okay, but this function here is not the same. This periodic growth model here is not the same as that periodic growth model in part A. You see, this is such a short base, only 1.03 exact. But the other one was in 5 decimal, it was 1.03045. 1.03045. Somebody may blame on the rounding right here that, hey, if we round this down to 2 decimals and it's so close to 1.03, well, I agree, but in the end, I just want to point out those two are not the same functions. Okay, so if you take 5 decimals here and only 2 decimals for 1.03 and you put it on the graph, it's still going to show, I mean, maybe at some small interval of t it will be the same, but at some far interval you will have some noticeable difference. Okay, and so that is how we get our the example 3 done right there. All right. All right, and now we can even get into another example, okay? And to continue as a continuation in this particular lecture right here, let's call this example 4 right here, another problem where we learn to write our own modeling function, our own exponential model function right here from the given information. Okay, so let's say this is example 4, and then after writing it down, I am going to swing over to the computer screen right there, to the computer and show the worded instruction of the problem, the worded description of the problem on the computer screen. Okay. All right, so here we go. This is now the worded description for example 4 right here. So let's start reading it. The population of ants initially with 1,000 of them, okay? And so for short, I'll just write initially with 1,000. So the population of ants initially with 1,000 in a colony grows and then stops. I mean grows, and then I stopped my description right there. Okay? And so now that's all we know over here. We know that it's going to be a growth according to that wording right here. We know it has to be an exponential growth. It's a population growth like there. And then we now have an initial quantity. We know an initial population, okay, and we know it's a growth, and that's all we know. All right, and so now let's get to part A of the question particularly. Okay, so initially with 1,000 ants right there, and it grows, but now this time here is the situation. In this part A, the situation is that the population grows continuously. So this is a continuation to the sentence there really. So the population of ants initially with 1,000 in a colony grows continuously by 4.2% per month. All right, and so now allow me to indeed undo this highlight right here and put down again some other highlight in a more broken up way right there so that it catches our attention a little better. So now we have a rate right here, a growth rate, but it's clearly indicated it's a continuous growth rate. All right, because if we put the entire sentence together from here to here, I'm looking at the population of ants initially with 1,000 in a colony grows continuously by 4.2% per month. So this is clearly a rate, okay, 4.2% per month. It's a rate, and it's a continuous rate. And now this word per month right here is indicating that this is our default time period. But so in this particular kind of problem, since it's growing, the population is growing continuously anyway. Okay, so we don't really need to pay too much attention to that term per month like that. But now we have enough information to write it down right there and to start sketching down the problem. So now let's call that Q here to be, or how about, I'm getting tired of Q, so let's call it P for population. So the population of ants here is a quantity as a function in terms of time. Okay, so the population size, okay, in some t months, okay, after the initial point, of course. All right, and so now according to the given information right there, then, and this is also independent with any part right there. So really, so p of 0 at 0 time right there, p of 0, or the initial time, we know that it's 1,000 ants, okay, at start. So now I'm not gonna beat around the bush by writing down too much worded description anymore, but this is p sub 0, okay, p of 0 equals 1,000, because that's the initial amount. All right, and then, yes, time is in month. T is time in months. All right, T is time in months. So now, what matters for us here in part A? In part A right here. So this is just general descriptions that we already knew. But so in part A right here, we know that our rate was given, so let's write it down right here. It's a continuous rates, okay? Our population of ants is growing, of course, so it's a growth, but it's a continuous, okay? It's a continuous growth rate. All right. It's a continuous growth rate. And that is, so now with this growth rate, let's use K. Let's get straight to that. So it's common enough throughout textbooks, including the textbooks written by Professor James Stewart, that we use K as the continuous growth rate. Continuous growth rate right there. Okay, in a continuous growth model, whereas we're using just the traditional lowercase letter r. Okay, for the periodic rate. Okay, so here I'm going to get straight into K equals 4.2% per day. Or another way of saying this is K equals 0.042. That's what we have. All right, and so now once we clicked with that word right here, I wrote it in red, so it's so clear. It's a growth rate, and it has that extra clarification that it is a continuous growth rate. And so now we get straight into the model that's suitable for this. So out of the two models, the continuous growth model has to be the one that's more direct right here. That's directly that comes directly out from this. Okay, so now P of t, we have to use this model right here. P sub 0 times e to the kt. All right, get for yourself into that habit of always write down the actual form of that model you're about to use right there. All right, and so now P of 0 is this. And I could have also notated that this is also the same as p sub 0, like that. The same as p sub 0. And so now k is this value, and p sub 0 is this value. It's the function value at initial point, initial time. So now we're ready. Okay, so here it's p of t turns out to be 1,000 ants, but it's in some t months later, it's going to raise by this model 1,000 times 0.042 t. We're done. And this is, of course, a continuous. This is continuous growth model. All right. Continuous growth model. That's what it is. All right, so now let's now look at part B of the example. So all of that beginning description is retained the same here. So we have a population of ants that initially started with 1,000 of them, and this colony grows. So now in part B, we're in a different situation right here. It grows, but grows by 4.2% per month. All right, and yes, similar the requirements right here, similar task right here. We want to write a model which represents the population of the colony after t months. So now see that here is indicating that the default time period here is month. Okay, so now, but the growth rate here, it's a growth, but the growth rate given here comes without the word continuous or relative. So that means this growth rate right here has to be a periodic growth rate. Okay. So now let's sketch down the information on this board of mine right here. All right, so we can still use some information from the beginning part where I wrote on the other board, because we can still call that p of t here be a function that models our population size in some t months. We still have the same initial amount, and t is the time in months, like that. So we can retain all of that information above this line. Okay, so now when it gets to part B in particular, all that changed the situation is that the rates here we have is simply just some growth rates right here, or some general growth rate. Nothing special, and further, it's not a continuous growth rate. That's what's important. All right, so now for this kind of growth rate right here, it's just simply a periodic one. I can easily see that now, okay, because there was no continuous attached to it. There's no indication that it's continuous. So automatically we can understand that it's a periodic growth rate. Okay, so now I'm going to have to use, I can't use K. I have to use R. So R here equals the 4.2% per month, and this is the same as per month. Per month. Okay, and it's the same as 0.042 per month. Okay, and so now in that way, clearly speaking, it's a periodic growth rate. And so there's, of course, among the two choices, the continuous growth rate and the periodic growth rate. I mean the continuous growth model and the periodic growth model right here. The periodic growth model will be the one that's more directly with this problem, more directly suitable right from this given information. Okay, so again, as a reminder for yourself, the periodic growth model is in the form of Q of t equals Q sub 0, the initial amount, times 1 plus R to the t. That's all there is. That's all there is. All right, and now our periodic growth rate is here, 0.042. Okay, and then we already knew our initial the population. So now simply it's just Q of t equals 1,000 as the initial amount, the initial population, times 1 plus 0.042 to the t. Ideally, theoretically, we're done at this point, but it would be a better idea to add this and come to a finalized version right here. So Q of t in the end is finally 1,000 times base 1.042 to the t. That is how simple it is to come up with our periodic growth model right here directly from the given information. Okay, so let's call this is the periodic. And so the question did not clearly indicate that which model we have to use, but now it is our responsibility to know how to make the correct choice right there. And it's not really right or wrong, but it's the choice that's more direct from this. Okay, so the periodic growth model. All right, so at this point, after example 3 and example 4, the rule of thumb here is that if the problem gives you immediately periodic growth rates, then periodic growth model would come out a lot more direct. And I'm not saying that we cannot find the other model, but this one here should be the one that comes first because it's a lot more direct. Anytime your problem gives you at start the periodic rate growth rate, okay. Whereas in this case right here, anytime the problem of yours indicates for you that the growth rate is a continuous growth rate. It's a continuous growth rate right there. Then we're gonna go directly into this form with base E right here, because continuous growth model in base E is the one that's more directly with that, because we have all the information directly given here already. All right, and then from there, if we have to re-express our function in other bases, then we can proceed afterward. All right. All right, so, and now we're still gonna get ourselves into another example where we're gonna continue learning our skill, building our confidence, our foundation on writing our own modeling function based on the given information. Okay, so let's now head out for example 5 right here. Let's call that example 5. And again, just like the earlier two examples, I am going to, after I write down the label of the example, I am going to swing over to the computer station and put the actual worded instruction of the problem on the screen like that. All right. All right, so here we go. So now what we have here, according to this description, and it's a very beginning description right here, so nothing much yet. And the sentence is not even completed yet. Okay, just like the earlier example actually. So starting out with 20 milligrams of a radioactive element. You will need to take a formal course in chemistry to understand what exactly a radioactive element is. But it's just basically, for anyone as the minimal, I can just explain a radioactive element just simply means an element that's easy to break down and disappear. That's all there is. But why it's like that and what causes it like that, you must take a formal course in chemistry to understand why. Okay, and how we can see that as a radioactive, like that's is the role. That is why you need to learn formally with a chemistry professor. Okay, so now back to the problem itself. All you understand here is that it's some elements that can break down and disappear easily. That's why now 20 milligrams at starts. Okay, and then it reduces. See, so the way how it's stated here, 20 milligrams of a radioactive element reduces, and that's why I'm using that term right there. But so now right here with this term reduces, what caught my attention is we're no longer working with a growth problem. So we'll get ready, in this example, get ready for an exponential decay problem, Okay, so we've been doing exponential growth in example 3, exponential growth in example 4, and now let's get some good experience with the exponential decay. Okay, and that's why, you know, what caught my attention there, what caught my attention to decide that it's a decaying problem is that the word right here is reduces. So over time, yes, started out with 20 milligrams, but over time, okay, it will reduce itself, and we're gonna learn to come up with a model to predict, you know, how much remains in some amount of time t later. All right, so after that, let's now head out to the actual question. All right, so now in part A, so we knew all of these information right here, 20 milligrams at start, right, and it reduces, indicating that it's an exponential decay problem, but it reduces about 15% each day, 15% each day. So now we have a rate, and then in this problem, it's a decay problem. It's an exponential decay problem. Okay, so clearly now we no longer call this a growth rate, but we call this a decay rate right here. So so basically this element, for whatever it is, it's going to disappear about 15% of them each day. So the term each day here is also indicating that our default time period is in days right here. Okay, so the elements disappearing about 15% each day. So now our task for the function, write a function. So now our task for the problem is write a function that models the amount of elements remains in t days. All right, so just like that, t is in days, okay, in t days. Okay, and then, but wait a minute, there's some extra information right here. So there's the same question, but there's another the portion of the problem that's asking for something extra. So we'll get to that later. Okay, but now let's come up with our function up to this point here. Write a function that models the amount of elements remains in t days. All right, so in that way, it's an amount of radioactive elements. So let's call that a quantity Q again. Okay, because it's just me maybe that I like to use the term quantity and quantity. All right, so quantity Q of t equals, or we call that, we refer to that as the amount at, how about this time I'm going to change the wording a little bit, the amount at time t. Okay, and I don't think we need to jump down to that lower line with that. So let's save for ourselves more space. The amount at time t, because hey, it's a decay problem, and so of course in some time t later, it's whatever amounts, that's basically the amounts left. So all we have to indicate is the amount at time t. Clear enough. All right. And so now, even before we got into the problem, we can extract out some universal information. According to the way how I see it, it started out at 20 milligrams and it reduces itself. So that 20 milligrams clearly has to be the initial amount. So Q of 0 equals 20 milligrams. Okay, mg stands for milligrams, and we can also see this as our Q sub 0. That's the initial amount right there. The initial amount. All right, and that's everything we have. And so now I'm going to draw a line to separate it out right there, because that's sort of like a section that's listing out the universal information regarding the problem. So now let's get ourselves into part A of the example. So for part A, we're looking at one more time back on the worded instruction of the problem. The element reduces about 15% each day, 15% each day, okay? And we want to write a function that models the amount of elements. So now, once again, it's a rate right here, and this is going to work very similarly to how it was before with the growth, exponential growth problem right here. Mainly my point here is that the rate described here is not indicated, nowhere indicated to be a continuous or relative rate. Again, the rate described here is not indicated as a continuous rate. So by default, we can just simply understand that it's a periodic rate. And so in that way, at this point, after you have built some good experience already, we can just head straight into the periodic growth, periodic decay model right there. Okay, and so again, just that rate right there is a continuous, it's a periodic rate. It's a periodic decay rate. All right, and so we're going to head straight into, after recognizing that it has to be a periodic rate right there, then we're going to head straight into using a periodic decay model. It's a decay problem, so even if I accidentally say growth, like that, sometimes throughout this example, the truth is the truth. It's a decay problem. Okay. So now I'm just going to simply say decay rates right here, but no extra clarification that it's continuous or relative. So it stays as periodic decay rates. Okay. Or let's put colon here. Colon, and this decay rate right here is, of course, I have already recognized that it's periodic decay rate. And so now I can see that I have to use the letter R right here. R equals, so it's 15% each day. So 15% each day, okay? Each day. So what we have here really is 0.15. It's 0.15. R equals 0.15. All right, and so just in my arguments earlier, it's easier for this particular case right here, that it's easier and a lot more direct, that we head straight into that periodic decay model right there, periodic decay model. And so what does the periodic decay model look like? Q of t equals initial amount Q0 times 1 minus the rate. So anytime it's a decay problem, anytime it's an exponential decay problem, and we've learned this way earlier in this particular lecture right here. So Q sub 0 times 1 minus R to the t. This is the general form of our periodic decay model right here. And of course, it's an exponential decay model. All right, so now in that way right here, then we'll simply just throw in Q of t equal. So now the missing piece here is that 20 milligrams. Let's put it in 20 milligrams. All right, and as a matter of fact, I do not need, and I shouldn't put units milligrams in there. So 20 times 1 minus 0.15 to the t. That is, ladies and gentlemen, at this point, that is our finished point of the periodic decay model already. But we would like to go a little further in terms of subtract these two values to come up with one simpler base like that. So 1 minus 0.15 is going to give me, so my final expression here is 20 times a base 0.85 to the t like that. That is our periodic decay model right there, and this is the function that models our quantity, our amount at time t. We're done with that function. All right, and so but I'm going to leave a little space here. We're done with that, and it starts out in this particular model that we finished right here. It's a periodic decay rate. Okay, and so now. But now before we move on to part B right here, then all of a sudden what caught my attention here is that in the same part A, there's another question. What is the continuous decay rate? So the question, this part A right here, is not asking for the function in continuous model, but it's still asking for the continuous decay rate. According to this question right here, what is the continuous decay rate? All right. And so, understanding our goal now, continuous decay rate is that k value. So we want to find what's the value for k. That's what we want to look for, the continuous decay rate right there. Okay, or the relative decay rate. Because, okay, this is the rate from q equals q0 times e to the kt. That's the one. All right, but now how do we find that? So now in that way, allow me to remind you, 1 minus r will be equal to e to the k. That's how it is right there. 1 minus the periodic rate, 1 minus the periodic decay rate will equal k to the continuous decay rate, e to the k. All right, and we're in a position to find k right there. And by the way, 1 minus r is 0.15. So 1 minus r, isn't it that obviously it's that 0.85 right there, 0.85 that we already found. So 1 minus r is 0.85. So now to complete this equation, I'm looking at 0.85 as a value that equals e to the k. And again, our goal is to look for k. Our goal is to look for k. This is an equation. This is an equation in exponential form. Okay. So now, in order to find k, we're just simply going to rewrite this equation in logarithmic form right there. Logarithmic form. So at this point, k equals natural log of 0.85. All right, k equals natural log of 0.85. Natural log of 0.85. And so, ladies and gentlemen, again, just like what I said, there are about 20% in every problem, every exponential application problem, exponential function application problem. That 20% in each of those problems will be a logarithm problem. All right, so if we're looking at our example 5 here as one exponential application problem, exponential function application problem, then there has to be at some part here and there will be some logarithm problem involved. This is where. All right, so now I'm going to swing over to my calculator on the computer screen and get the value for that. Okay, but you can also leave this in exact form right here as well. Okay, but then in case anyone desires an actual decimal, I'm going to swing by the computer and grab that value. All right, so on my calculator, now I'm going to go ln of 0.85. Okay, and this time it should be a negative value. Negative 0.1625189 and a lot longer. All right. And so allow me to use 5 decimals. So it's approximately negative 0.16252. All right, and that's the value right there. Negative 0.16252. That's what it is. So that's the continuous decay rate right there. All right. And so now the same example over here. Let's look at part B. Let's look at the different situation in part B. So what if this 20 milligrams of the radioactive elements reduces, and we found out that it reduces continuously at about 15% each day. So we have a rate, and further this rate is clarified to be a continuous rate right here. And it's a decay problem because the element is reducing itself right there. It's losing itself about 15% each day continuously. So now it is evidently that this is a continuous decay model is going to need to be used here, which is a lot more direct. So, and this rate right here itself is a continuous decay rate right here. Okay, so now I'm going to head back on the board. All right, so some universal information from the beginning can be reused again. All right, so let me quickly swing over to the other board again. So Q of t is the amount at time t right there, and then Q of 0 equals 20 milligrams. This is the initial amount right there, and then everything below this line was already done. We found the function that in the periodic model right here. Okay, but now in our problem here are part B, and just think about if we are doing this problem completely from scratch right here without seeing part A, then, and treating this problem completely as one independent problem on its own right here, then yes, we still want to eventually write a function that models the amount of the elements that remains in t day right here, okay, in t days. But this time we have to stick with the continuous decay model over here, because the rate right here is indicated, as I explained earlier, it's a continuously, it reduces continuously about 15% each day. And so now I know that my decay rate, and this is for part B of our example, so our decay rate here, okay, and the wording is making it clear. So this is now recognized as the continuous decay rate. Okay, so now I have to use the variable k for that. So k equals 15% per day. But when it comes to continuous decay or continuous growth, and it shouldn't matter, it shouldn't be too important anymore about the default time period right there. But we can just still write it down. So this is per day. Okay? Or in other words, k equals 0.15. Okay? But it's a k value. It's not the r value. All right. And so now we are ready for, and upon realizing that this is the continuous decay rates, it's a lot more direct, right? And it's the first thing in line right there, the most direct. The model to use here is the continuous decay model, the continuous decay model. So here I'm looking at q of t equals q sub 0 times e to the minus kt. Okay. All right. So q of t equals q sub 0 times e to the negative kt. So I put a negative here because I know it has to be a decay. And in the end, because our rate is always written as a positive number. I mean, a lot of times when the problem is describing to us, then we're always going to take the value here as a positive value. And then, okay, and then if it's a decay, then we put a negative kt right there. So that's one way of saying, or you can write kt, or you can write k as a negative number if it's a decay problem, and then you just write q equals kt. Okay, that's one way. So I chose earlier, it's just a random choice, but you can also choose to write differently. So it's just for decay problem. When it's the decay problem, you can decide to write your k as a positive number, okay, for a decay rate. But then in your continuous decay model, you have to write minus kt, okay. And then if you write your k, for example, if you write your k as a negative 0.15 because you already knew that it's a decay rate right there, then you can just simply write q of t equals q0 times e to the kt. The point now is that the coefficient with the k has to the coefficient in the exponential, in the base e exponential has to always be negative because it's decay. Okay, so two different, slightly different situation right there, but you can make your choice on that. I'm not particularly against any one of the choice right there. So here I wrote k equals 0.15 as a positive number. Then in my decay problem, the decay model over here, continuous decay model, I have to write q sub 0 times e to the minus k. All right, and then once we've got that cleared out, then it's quite ready for us. Q of t, the quantity in time at time t right there, the amount of the radioactive elements that remains at time t is going to be just simply 20 milligrams at start times e to the minus 0.15 t. We're done. This is what we call the continuous decay model. Continuous decay model. Okay? And it didn't take any steps at all. It took me some explanations and all that, but in the end, getting that there, and once you are fluent with that, it's going to be a lot faster than what I did here on the board. Okay, but now let's look back at the problem here, because I noticed earlier that there's something else after coming up with the function right here. Okay, there's something else. There's another extra question in the same part B, but after we're done with writing down the question. All right, and so now in this problem right here, after writing the function that models the amount of elements in t days right here, the next extra part is asking what is the decay rate. But now since the rate here was already given as a continuous rate, and so now this decay rate without a clear indication, without an indication, then here it's intended to be the periodic rate right here. So if the continuous rate was already 15% each day, then what can be found as the periodic decay rate right here? All right. So now back on my board, the task is quite simple. So when it's a decay problem, like I said, the only thing is that we have to make choice. We have to make a choice between whether we're writing the k here as a positive or negative. So I already wrote my k here as a positive, and it's not a rule. So it's just me. Maybe in the next problem I'm going to write k being a negative for a decay problem. It's simply just a choice. But you have to keep in mind, if your choice written from start right here is a positive k, then in your continuous model it has to be a minus k. Okay? And then if your choice is a negative right from the beginning, k equals a negative number, then you can just write q of t. As I said earlier, if k was written as negative 0.15 in your choice right there, okay, because it's a decay, and so then your model function can be written instead 20 times e to the minus 0.15. So it's, once you put all the numbers together, then it's the same. It's exactly the same. It's just generally speaking. It's q sub 0 times e to the kt by skipping the negative sign here when you already wrote your k as a negative. And that's the idea right there. So now just be careful with that. And that's the only thing. But now once you know what you're doing with your k, once you have already known what you're doing with your k, then so the only relationship. So think about this. In our problem, I chose to write k as a positive number. So mainly in this continuous decay model that I'm writing, then it's about e to the minus k. E to the minus k has to equal 1 minus r. That's simply it. E to the negative k has to equal 1 minus r. 1 minus r. Okay? That's the decay rate. But then, and further, be careful in a way that in this problem, we actually looking for just the rates. We're not looking for the other model. So this is the continuous model, and in some other problems, the wording may ask you, according to the description of the problem, the problem may ask you to find the actual periodic model. But here, the problem is not asking you for the periodic model. It's only asking for the periodic rate right here. So now we have to solve for that rate carefully. Okay? So now I'm looking at, so that means from this equation, we're looking at 1 minus r equals e to the, and minus k here. See, k was written as 0.15 positively. So minus k here is going to give me e to the negative 0.15. That's all. Okay? Negative 0.15. And then from there, at this point, we don't need any logarithmic operation here indeed, because e to the negative 0.15 is already itself just simply a value. I mean, admittedly, it's not a nice looking value, but it's already a value. So here we can just simply rearrange this equation and solve for r, and r is going to be the periodic decay rate right there. Okay, so now I'm gonna, before I head over to the calculator, I'm going to just simply rearrange this, taking account that this is already a value right here. So that means rearranging side by side, I'm looking at 1 minus e to the negative 0.15, because I subtract this known value to the other side and add this r to the opposite side. So that's r. So r equals, I'm reading backward with this equation, r equals 1 minus e to the negative 0.15. And now we are ready to come up with the final calculation. All right. And so now on my board right here, on my calculator right here, then we just go 1 minus, and then here it's e to the negative 0.15. All right, and hit enter. This is now our final rate here. This is our, and I mean, I should have said periodic rate, periodic decay rate, periodic decay rate. All right, so that's the value. And so now I'm going to write it down in about 5 decimals. All right, so R equals 0.13929. All right, that's, and a lot longer, of course, but that's about good enough for us here. All right, so, or we can see that this is about 13.929%. You see, so it's quite different. It's quite, so here the periodic rate is quite different with that, the continuous rate right there. And of course, it's definitely not the same with the one in part A. These are just completely two different problems already. All right. All right, so at this point, after seeing enough, we are going to continue going into some more examples where we're still going to learn to construct, to write our modeling exponential function. But now we're going to allow the problems to become more advanced. We are going to put ourselves in some more, a little more challenging situations, okay? Because the earlier examples from example the 1 up to example 5, we derived the function, we came up with the function from quite direct information. But now allowed me to put you into some of those problems where the information given is not as direct. And then from there, we're going to learn to extract the information and build our function, okay? And write our function that models according to the given information. Okay, so now let's call that example 6. All right, and then once again, just like any of the earlier example, as soon as I finish writing this down, I'm going to turn over to my screen at the computer station right there and put it on the actual screen, and we can all read the reading description of the problem together. And this time now, it's each example is one complete problem. All right. All right, so here we go. So in this example 6 right here, according to the problem, it states the following. It takes 225 minutes for 250 milligrams of a radioactive element to decay to 32 milligrams. And then that's the end of the first sentence there, and that's the only sentence here. And then as a goal of the problem, as for what we are asked to do, find a function that models the amount of the elements in t minutes. The amount of the elements in t minutes. So now, as the wording here was stating clearly right here, this problem here is a decay process. It's a decay process. It's a radioactive element, and so it's losing on its own over time. All right, so now according to the wording right here, we don't have a decay rate given directly. Okay, we don't really have a decay rate given directly here. The only information that reveals some truth about how fast the decay process takes is that it takes 225 minutes for 250 milligrams of the elements to decay to 32 milligrams. That's all the information we have. And so, again, we have clearly no clue. We have no clues about the rates. Okay, and then so at this point right here, it's time that I give this advice right here. We can start departing from the worry about the default time period, So the main time period here is in minutes, as you have already seen. The main time period here is in minutes. And we learned that it takes 225 minutes for 250 milligrams of radioactive elements to decay to 32 milligrams. So let's read a little more closely into the wording right there. from 250 milligrams and it decays to 32 milligrams. It gives me a clear impression, it gives me a clear understanding, at least, that 250 has to be our initial amount. 250 has to be the initial amount, the quantity that I highlighted there. Okay, and now so we don't even have to worry about is it going to be a 10% per minute or a 20% per minute as those usual problems we have seen back in the earlier examples anymore. But here it's just something, we have some clue leading to how fast it goes, and we don't even have to make judge about how fast or how slow that is. We just simply have some clue to indicate some ratio, some rate about the process here. Okay, because according to the wording description, then we know a starting amount and some ending amount over a certain period of time. 225 minutes here is a certain period of time. And we know a starting amount and an ending amount. That's just be enough for us to find the rate. Okay? And so we don't even have to worry about whether this rate, this description of the rates. I don't even say that it's a rate anymore. Of course, there's a rate behind the scene, but I would just say this is a description. What I highlight here is simply a description of what the rate is. And so at this point, I even advise my students, anyone viewing the lesson, that we can even let go of the worry about the period. Is it a periodic rates, periodic decay rates that's given in a problem, or is this a continuous relative rates that's given in a problem? I'm going to completely let go of all that. One thing we keep for sure. Here, the process itself has to be a continuous process. The elements will continuously break down. Every instance we will lose some amount. All right. And so now in that way, let's come up with a plan of how we can handle a situation like this. Okay. And so now back on my board right here, let's call the quantity in my, well, I favor using Q for quantity, so I'm going to call that Q of T here is the amount in T minutes. All right, it's the amount in T minutes. And now, after that, I see, so I stated earlier and I pointed it out earlier, we had a starting time and an ending, we have a starting amount and an ending amount, so we can tackle down right there for Q of 0 has to be 250. So 250 milligrams here, the start of our time interval, and then 225 minutes later, it's going to decay down to only the 32 milligrams left. Okay, and so now we can clearly use this as our initial amount right here. Okay, so now as a notation, it's Q sub 0 equals 250. We have for ourselves an initial amount right here. All right, so periodic decay rate, we don't know. Relative or continuous decay rate, we don't know as well. Neither one of this is given to us. Neither one of this is unclear. And so now, this is now also another advice, and this is another the explanation of mine that comes in right here. Well, after all of those examples prior to this particular one right here, up to example 5 I've done earlier, and I've been giving my students, my learners, the impression that we have two models to write. We always have two equivalence models to write. If we stick with the R right here, and this is a decay rate, then we're gonna go with Q sub 0, the initial amount times 1 minus R raised to the T, where T here is in minutes. Okay? Or we can make a choice to go with relative rates or continuous rate here, and we call this a continuous decay model. Q of T equals Q sub 0 times base E to the KT right here. We can make a choice here. So now, when we're completely in a situation like this particular problem right here, when we're completely clueless, or it is completely unclear about whether we already had, whether we know the relative rate or periodic rate. None of these is clear. None of these is given directly. None of these is clear. I mean, we have some information behind the scenes according to the worded description, but none of these is clearly given. And so in that way, now allow me to point this out right here. We can still make any choice here, but in my years of working and also working interchangeably with the scientists out there, the chemists, the physicists, and the biologists right there, I noticed that the majority of scientists out there would use directly from again, provided that so little known about the rates here, what kinds of rate that is. We are completely unclear about whether we have a continuous rate available or we're having a periodic rate available. None of this is clear for us. Okay, and so in what I have seen and noticed throughout my years working together with the scientists, the chemists, the physicists, and all that, and I've noticed a larger percent, the larger group have more commonly used or headed directly into using the continuous model. So the continuous models as a majority out there has more attention. Okay, and when you arrive at your calculus work, you will see better explanation of why using base E will be more advantage. All right, so now allow me to lead this example right here in the way that base E wins in terms of this one right here, it just simply wins in terms of it winning the attention because in the later classes it's a little more, it will actually be quite more convenient to use base E, and you will learn that convenience when you arrive at the calculus course. And so now for that reason, allow me to ignore using this form right here, but I'm going to stick with this continuous, this is a decay problem, so I'm going to stick with the continuous decay model right here. Okay, but simply it's just a choice that I'm going with a larger majority of scientists and mathematicians out there. Okay, and so now I'm going to erase this, and we don't need to worry about the periodic rate. So now I know that, but still in the end, choosing to go with that model in base E doesn't mean we already know the K value. But that just simply means we're starting out completely from scratch. We have to find out what our rate value is, what our continuous decay rate is. All right, but now if we're looking a little closer, then we have quite some good amount of information given already. The initial amount is here. Okay, the initial amount is here. And then I just now realized I forgot to put in one information. Now, it was stated according to the form that it decays, the material decays to, or how about, according to this information, the element decays to 32 milligrams in 225 minutes. All right. So let's take good notes of that, and then I will get back and explore more information out of that statement like that. So now in this particular problem, the initial amount is here 250. So our function here comes to Q of t should be 250 times e to some relative rate and t. So 250 times e to the kt, where k is our to be found relative rate, our to be found continuous decay rate. All right, and so now what's useful about this statement I put on the board right here? The element decays to 32 milligrams in 255 minutes. The element decays to 32 milligrams in 255 minutes. And this is just a different interpretation of the information we read from the computer right there. But now in that way, this is the quantity. This is how much the quantity is when it's 225 minutes later, after the initial time. Again, this is how much the quantity remains. This is how much the quantity of the elements remains after 225 minutes have gone by. And so in that way, into this functional concept right here, I'm looking at when it's the quantity will equal, or another, before I'm getting into that, how about from that interpretation here, I see the quantity at 225 minutes equals 32. This is the mathematical understanding of this statement here. The element decays to 32 milligrams in 225 minutes. We call our amount here, we call our quantity here the Q of t function. So the quantity in time t like that. So now when time at 225 minutes later, the quantity becomes 32. All right, so in that way, we're going to directly take this information. Okay, and now this is what I can do. Q 225 means on the right-hand side of this current equation of mine, I can have 250 times e to the k times 225. Okay, so that's the time right there in minutes. And then on the left-hand side here, that equals 32. So now, at this point, ladies and gentlemen, I have produced for myself, and how about in one more step right here? Now I can take away this information to maximize my board space here. But at this point, I have the following equation. 250 e to the 225k equals 32. It's now an equation in exponential form. It's an, or right out of the box, this is an exponential equation. It's an exponential equation, and the only unknown we're looking for, the only unknown we're solving for, is this value for k. So think about this as a little bit of a thinking ahead right here, but once we're done solving for k right here, that will be our continuous decay rate. And if it's a decay, I am expecting that the k value here has to be a negative value. All right, so now let's go ahead and head out further. So now I'm going to go ahead. This 250 on the left-hand side is only a coefficient. I am going to divide both sides by 250. Okay, so I'm looking at e raised to the power 225k equals 32 over 250. And now clearly this is not only an exponential equation, but this is an equation in exponential form. An equation in exponential form. All right. And we can further reduce this 32 over 250. Okay, to make our work a little easier, we're going to reduce that to 16 over 125 right there. Okay. All right, but now again, back to what I was in the middle of saying, this is an equation in exponential form, an equation in exponential form. So in that way, we have learned, and this is where, again, this is where logarithm is applied. This is where our understanding of logarithm applies here. Okay, because as I've been saying a few times throughout this lecture, in any problem that we're doing with exponential function as an application, about 20% in the problem, about 20% in each problem will be where we apply our logarithm understanding to solve the problem right here, and this is part of it. Okay, so now from this equation right here, we can quickly rearrange this equation into logarithmic form. So now I'm looking at natural log, or how about I can rewrite this as 225k equals natural log of 16 over 125. It's just simply, we rewrite this equation currently in exponential form into the new equation where it's now in logarithmic form like that. All right, and so now the advantage of doing this, now we can see that the variable now is as a linear term, and we can just divide both sides by 225, and that will get us the answer. And so now continuing a little further, and then allow me to write my continue work on the next board space right there. All right, so now in that way, currently I'm at 225k to equal natural log of 16 over 125. Okay, and so now, and I I still want to move on with the algebra instead of rushing into punching it in the calculator. And so solving for k here, we're just going to divide both sides by 225. And so consequently, we will end up with the value for k to equal 1 over 225 times the natural log of 16 over 125. Okay, but now so this is our answer. But I said earlier that the answer is going to be a negative. So to convince anyone that this is a negative answer, now let's type it into the calculator. Okay, so now on our calculator, we have 1 over 225, and I should have put that in parentheses. So in parentheses 1 over 225, okay, and multiply with natural log of 16 over 125. All right, and so now this is my answer right here. It's a negative 0.0091365 and a lot longer. All right. So now in about 5 decimal places, we have found the relative growth, the relative decay rate or the continuous decay rate right here. So k equals negative point, or approximately, I should have said that. All right, so approximately negative 0.00913, and then in 5 decimal places, 37. And this is now making it clear that it's a decay process right there, because the value. So there are instructors who are allowing their students to write the final answer in an exact expression like this. I'm not against that as well. I'm not against that either. Okay, but in a problem like this, it would be a little more beneficial to write the decimal expansion of this so that we can display the negative nature of our the decay rate right there. Okay, our whether the continuous or periodic decay rate. Okay, so now it's a negative value. So now we come to our final function right here. So now our final modeling function, q of t equals 250 e to the minus 0.009137 t. That is our final function that we were looking for. Like that. This is the function that models, or that models the amount of that radioactive material in some t time, in some t minutes right there. All right. And so, still in example 6, allow me to really keep the information very very brief, as brief as possible. But so we had q sub 0 being 250. We have our time here is in t is in time in minutes. Okay, and we have the quantity saying that when it's 225 minutes, it equals 32. Okay, so with all this information, now let's say what if we wanted to go with the other form? Okay, what if we want to go with the other form? So what if we want to go, and the other form I meant the periodic form right there. Okay, so periodic model. So what about that form? Like this is extra, even though, so technically at this point we're done with our example 6, but in case anyone would like to know. So coming with the periodic model, one way we can do directly, if we are doing that directly out from the information given here, then here's how we can do it. Yes, recall that the periodic model has to be q of t equals the initial amount 250 times 1 minus r to the t. What challenges us here is that we don't know the value for r. This constant, this rate of decay right there, okay, this periodic decay rate. So, but to find out, it's not that challenge as well. We already knew this important relationship. The amount reaches down to, or decays down to only 32 when in 225 minutes later. So now in that way, I'm looking at 32 to equal 250 times 1 minus r, because r is our unknown right there, raised to the power of 225, because in this row right here, t equals 225. I substituted that in. The value at that corresponding time is 32. And so now we have an equation to solve for. So I'm going to divide both sides by 250. All right, to end up with 1 minus r to the power of 225 equals 16 over 125. Okay, and that's I'm talking about the direct route, that we're just extracting information right from what's given here and solve it out. So now to solve for r, this is not really exponential function. I mean, this is not really exponential any longer, because this is a power 225. Okay, and so a 1 minus r, the variable is involved here, so the variable is in a power form right there. So now for power, to undo power, we take roots. We take 225th roots right there. So that means I can have 1 minus r equals 225th root of that ratio 16 over 125. And to be honest, admittedly, we don't even have to go all the way down to finding r. We don't really have to go all the way down to finding r in this particular problem, because our main goal is to find the function, the modeling function. And the modeling function, more importantly, involves 1 minus r. The modeling function in this way right here, the modeling function using the periodic model, use this form 1 minus r. And so we're right here at that step. We are right here at that step where we find an answer for 1 minus r. So why looking for r? I mean, we look for r, we look for the rate if we have to, like in the other case where we have to find a continuous rate. Okay, but here, yes, ideally we're looking for the periodic rates, but the periodic rates will contribute as part of the base for our exponential function. So why going further? We can stick right directly in here, and we take the 225th root like that. So now that means 1 minus r. After taking the 225th root, allow me to swing back on the computer and show my calculator screen like that, to show my calculation. So now on my calculator, I'm going to open the parentheses, and then 16 over 125, and now being raised to the power of another parentheses, 1 divided by 225. All right, and now hit enter. This is the value for our 1 minus r. All right, so in about 5 decimal places, so 0.990905, so in 5 decimal places it's 0.99091 right here. All right, so now I'm ready to write this information back on my board right there. So 1 minus r is 0.99091. So that means if we're going with the periodic decay model, then Q of t is written as 250 initially, multiplied with the base 0.99091 raised to the t power. And we have an equivalence function. All right, so again, the question of the problem did not specifically ask for which one. So I'm showing both solutions in case, in every problem or in any assignments that you are doing, that you are being asked to do in different ways. However, now again, be aware that in my advice now, the base E is the base that's being chosen as with the larger majority of mathematicians and the scientists out there. Okay. So that means this model right here is more widely used out there among the mathematicians and the scientists. All right. All right, so now we are ready for example 7, another example where we're in a situation where, we're not clear about the rate and default time period anymore, but we're gonna still find our the function. We're gonna still find the modeling function. So let's now call that example 7. All right, so here we go. This is our worded description of the problem in example 7. All right, so reading the wording description right here, it says it took 1 month for 300 cancer cells of a type, whatever type that is, to grow to 360 cells right here. Find a function that models the number of cancer cells in t months. In t months right here. Okay, and so once again, the wording says it took 1 month. So we have some amount of time here. It says 1 month, but that really doesn't mean to give you a rate or whatever. Okay, this is just basically an amount of time, some amount of time here. It takes 1 month. It took 1 month for 300 cancer cells of a type to grow to 360 cells. So we have some initial amount and some ending amount. We have some starting amount and some ending amount. And it takes this much time, being 1 month, to grow from 300 to 360. Okay? And so that's all the information we have. So in other words, again, my point is that in this problem, similar to example 6 that we have done earlier, the rate was not directly given in either form. Relative rates, okay, or periodic rates. Maybe this gives you some impression about the periodic, something periodic because it's 1 month. But it's still not indicated as a rate yet. All right, it's still not indicated as a rate yet. So in the end, it's still unclear about whether we are given a periodic rate in a problem or we are given a relative continuous rate in this problem. R or K are all unknown for us right now. Okay, there will be clues for us to find out, but at this point right now, the rates are completely unknown. Okay, and so now, once again, that's everything we have right here. It took 1 month. So there's a time amount, and then there's a starting amount, and there's an ending amount. And so now on this board, allow me to write it down right here. So we want to find a function that models the quantity of cancer cells in some t months. That's what it was asking in the problem. So I'm going to say, let's call that quantity Q again. So Q of t is the quantity or the amount. Okay, the amount of cancer cells, all right, in t months. All right, and this problem is one problem that clearly exists in the daily work for the medical scientists right here, okay, or medical experts right there. So everything we know now is that Q, we can call that time instance where we started out with 300 cells, 300 cancer cells to be the initial time. So in other words, I'm saying that Q of 0 equals 300. We already have found out an initial amount right here at initial time t equals 0. So I can label this as Q sub 0 equals 300. We have that. Okay. And then from that wording I've seen earlier, it took 1 month for 300 cancer cells to grow to 360. So the time amount is 1 month, and it grows from that starting amount being 300 to 360 cancer cells in 1 month. And so now I'm looking at and allow me to start writing it down in only a brief way right here. So what another information we have is Q when t equals 1. Okay, equals 360. That's how it should be understood. Okay, that's how it should be understood as. Okay, so we got initial amount, we got some amount indicated at some t time later. This is when t equals 1. So I don't need anyone to see this as a rate or whatever. It's not even, it doesn't even have to be a rate. There will have to be a rate behind the scenes that leads to this, the amount right there that grows out, but then we don't need to worry about that yet. All I see here, this is a time, I mean this is an amount at some corresponding time right there. That's all we need to see. And so R is unknown, K is unknown, the periodic decay rate is unknown, the relative or continuous decay rate is also unknown. Okay, and so now I have had this explanation in example 6 earlier. So now in this time, allow me to really deliver the solution that we use, the model that's the larger majority of scientists and mathematicians out there are using, the continuous growth model. This is a growing problem right here. The quantity is getting more and more over time. Okay, so now I'm going to stick with the continuous growth model. So that means, so here we go. This is the general start. This is a general starting point for our continuous growth model over here. Q sub 0, the initial time, the initial amount times e to the kt. And do expect that at the end our k value will be a positive k, because it's a growth. Okay, so our k here has to be positive. All right, and so now in that way, I immediately know that my initial amount, my initial quantity is 300. So I can put that here in place of my q sub 0. So 300 times e to the kt. All right, and so now we can see that anyone viewing the lesson can see that I'm getting closer and closer to completing the equation. So as soon as I find out what k is, we're done. The relative rates, the continuous growth rates right there. All right, so now it's time to use that piece of information. When t equals 1, we grow that cell, those cancer cells grow to 360 of them, that population of cancer cells. Okay. All right, so that means when q equals 1, we're looking at t equals 1, so 300 e to the k times 1. I substituted t equals 1 in place of t right there, and that here equals 360. So 360 equals 300 times e to the 1k right here. All right, and so now in that next way, in that way, what I'm looking at now is 300 e to the k equals 360. I have an equation. All right, and so clearly speaking, this is an exponential equation, but in order to successfully solve that equation, because at this point, k in this equation is the only unknown that we need to find out. And yes, that unknown is making it perfectly consistent with the missing information we have here, because throughout the entire function up to this point right here, the only missing information we have, the only missing information we need here is the value for k, the growth rate, the continuous growth rate, and we're about to solve for that here. Okay, so now in this equation, I'm going to divide both sides by 300. All right, so that leads me to e to the k equals, all right, so now I'm going to cancel both sides by, a 10 and by a 3 right there, 6 over 5. All right, 6 over 5. And so now this is my equation in exponential form. It's an equation of mine in exponential form. Base e raised to some unknown value k and equal the value 6 over 5 right here. So now in that way I can solve for this by quickly turning this equation of mine currently in exponential form into logarithmic form of that equation. So now I'm looking at natural log of 6/5 divided by k. And now we have come to a value for k. So again, there are instructors out there who will allow the students to write the final k expression like this, the continuous growth rate like this, and I'm among them as well. Okay, and I'm not against that, but then in a problem like this, sometimes to make it look a little more scientific, then punching out the value into the calculator, and get a decimal would make it look a little more scientific like that. So now I'm going to swing over to my calculation and get an approximate in decimal. All right. And so now I'm looking at natural log of 6 over 5. All right. My answer comes out, my k value, this is the relative or the continuous growth rate for here. It's 0.018232. And a lot longer, but I'm only going to go with 5 decimal places. So now k equals approximately 0.18232. All right, and that's my relative rate right there. And so now in that case, the function will finally come to q of t equals 300, okay, times e to the 0.18232. All right, t. That's our final function. This is the one that needs to be put in the box. Yeah. Even though earlier when I came to the reaction rate, I also put them in the box, but that's just to highlight the important information. But then this is our final answer. All right, so that's how we've done example 7. And again, anyone viewing the lesson here can make your choice to go for the periodic model as well. But again, allow me to just stick with the model where a larger majority of mathematicians and scientists are using out there. Okay, so this is the model this is called the continuous growth model, where it's going in base E right there. And that's why I've been saying, so I start explaining that base E is the winner is ever since, financial math problems, when we were still working with those problems. And now outside of financial math problems right there, then scientists and mathematicians out there, a big majority is going for base E as well. Okay, so now in the end, it's further confirmed that the base E wins. The attention is the winner right there among all bases, the one that's most used. Okay, most commonly used right there. All right. And now we are ready for another example. And along with some of these examples, I should be able to point out a few the terminologies as well, more like scientific terminologies. Okay, so now in example 8 right here, I'm going to show the worded description of the example on the computer screen. Okay. All right, so here we go. Cesium-137. Some kind of chemical elements out there. So cesium-137 has a half-life of 30 years. Okay, once I get back to the board, I will explain what this half-life of about 30 years is all about. But now that's the end of the first sentence, giving some description right here. And that's all of the description. And actually we have some extra over here, beginning with 200 milligrams of cesium. So the wording here is making it clear, beginning with 200 milligrams of cesium-137. We want to write a function that models the amount of cesium-137 in T years. Okay. So this problem is where it's making it clear about what I said earlier, that we're in a situation where rates is completely clueless for us. There's no way for us to tell if this is some kind of a continuous rate or the periodic rate. That we don't even have to worry about. There is some clue leading to there are some clues leading to us knowing whether leading to us knowing that the process is going on, is changing. Okay, and have a sense about how fast or how slow it goes. But then as far as precisely writing down the rate right there, continuous rate or a periodic rate, none of those is given. Okay, and so now I'm going to get back on my board, on the other board. So it says we want to find out the amount of cesium-137 in in years, after some t years like that. So again, just like the other examples, I'm gonna define my notation over here. Let's say Q of t is the amount, okay, the amount of cesium 137, okay, in t years. And you see the wording of this problem. What makes this problem even more challenging than the other two, than the earlier two, is that we don't even know if it's a decay problem or a growth problem. All we know is a new term, a new terminology, a half-life of 30 years. So without a formal explanation to come, then at this point, think about in our thinking process, in our thought process, we have no clue whether the population here, whether this quantity will grow in t years or will shrink or will decay in t years. And that's the idea like that. So at scratch, all I'm seeing here, this is a changing amount right here in some t years. Okay, so now this is what half-life means. But how about before getting to explaining what half-life is all about, allow me to write down some other information. What we knew here is that the statement said beginning with 200 milligrams of cesium. Okay, beginning with, that's what it says right here, beginning with 200 milligrams of cesium 137. This statement right here that I highlighted here is quite important for us. It tells us that we already had an initial amount. Okay, so this time initial amount is given quite clearly. So Q of 0, when time is 0 year, we're looking at 200 milligrams. Okay, and yes, this is our Q sub 0 quantity, 200 milligrams, and that's all we know. And so now, what exactly is a half-life? Okay, and so half-life now, half-life as a definition, and this is a term that's very commonly used among the scientists. Like any scientist who studies about the chemical or and any natural process here. Okay, so half-life is the time. See, so it's really important that you got to highlight is the amount of time. Okay, the time it takes. Okay, so half-life is the time it takes to decay. All right, it's the time it takes to decay to half, okay, of the initial amount, for whatever initial amount that is. All right, that's how we understand what half-life is. So it's actually a convention to indicate just how long it takes for the substance or for the elements to reduce down to only half of what it was, okay, originally or initially. That's what half-life is. So now in this way of how I define it, in this way of how I give the definition, I shouldn't say I define it because that's not even my definition. It's just the definitions that the scientists are using and have been using. Okay, but now write out from this definition, write out from this understanding. And so for anyone learning from the lesson, if you need to take a pause and write down carefully this understanding, you're more than welcome to do so. All right, but now assuming that you have already copied down what this definition is telling you about the half-life, it also tells us another important fact. Right here, pay attention to this word right here. That means throughout the process, we will lose a quantity. We will lose quantity. So this is now going to be clearly a decay process. It's going to be a decay process. All right, so now allow me to erase this because I need more board space to work with. All right, so now after understanding what half-life is, it's the amount of time. It's the time, how much time it takes to, to decay to half of the original amount. Okay, half of the original amount. So now, one more time, I'm going to turn over to the worded description right here. So cesium-137 has a half-life of about 30 years. All right, so now let's have a closer look. After we have had some understanding of what half-life is all about, then that means in 30 years, whatever the starting amount will become only half of that. All right, so that means here as a further impact, if we have already seen this, 200 milligrams of cesium-137 as the beginning, as the initial amount, then that means in 30 years, we will have only 100 milligrams remain. Okay, one more time I repeat. If we are now considering 200 milligrams of cesium-137 to be the initial amount, then it takes 30 years, t equals 30. It takes 30 years to reduce down to only 100 milligrams. Or another way of saying, we will have the quantity equal to 100 when it's 30 years. All right. So right from that information, so the half-life equals 30, half-life equals 30, because this is the amount of time it takes to get in half. Okay, so half-life equals 30 means we lead down to the following important, information right here. Q, when t equals 30, Q of 30 equals, but see, half of the original amount. The original amount is here, the initial amount is here. Half of that is only 100. We already got that clue, that precious clue right there. Okay, so now I'm talking about 100. Okay. So now I'm talking about, let's construct our function. And again, I am going to stick with the continuous decay model. This is now a decay model. And so, and again, just like the earlier two problems I brought up right there, we don't know the rates. And I am going to stick with the continuous decay model right there. That means I need to know what the k value is. But anyway, at the start, we can always write it as following. Generally speaking, any quantity that decays exponentially can be written as q sub 0 times e to the kt, but eventually expect that k will be negative because this is a decay process. We're losing quantity over time. Okay? And so now with that, I'm looking at further as some other information we have found here. We have q of t equals 200 times e to the kt. 200 times e to the kt. All right, so clearly we need to find out, and this equation of ours will complete once we have found out what k is. Okay, so now this next piece of information is useful here. When t equals 30, we have the quantity decays down to 100, which is half of the original amount, the initial amount here. Okay, so now in that way, 100 equal 200 e to the k times 30 years. All right, so substituting that information into our current the halfway done equation here, we produced this equation. 100 equals 200 e to the 30k. So now in my next space here, I'm going to write 200 times e to the 30k and equals 100. All right. So now in that way, I'm dividing both sides by 200. All right, and now I have, I produce for myself e to the 30k's equals 1/2. E to the 30k equal 1/2. And so now in this way right here, again, I'm seeing, just like many of the earlier problems we have done right here, this is an equation in exponential form. And this is a perfect place where we apply our logarithm understanding. So I'm going to rewrite this equation as, right, 30k equals log base e of 1/2. All right, 30k equals log base e of 1/2. And so now 30k equals log base e of 1/2. I'm going to utilize my space on the other board right there to write down our final k value and the complete function. All right, So k, at this point we're at 30k equals a natural log of 1/2. And so now we can solve for k here by dividing both sides by 30. Okay, so that ends up, that's ending up for us. K equals 1/30 times a natural log of 1/2. All right, and this is where I'm going to switch over to my calculator to get an actual value. So on my calculator here, let's look at 1 divided by 30 and times natural log of 1/2. All right, and dividing it like that, it's negative 0.02310496, and so on and so on. All right, and so now in that way, now I'm looking at in 5 decimal places. And that's just a choice like that. So when you're actually doing these problems where it has so much applications out there, make sure you look at your applications to see how far the rounding requirement is. All right. So here it's just mostly my choice like that. But when you're out there on your own field and doing your own work, that brings in the applications of these. Then you have to know how to decide your own rounding requirements out there that's consistent with your application out there. So here k is approximately negative 0.0231. Okay, 0.0231. That should be it. So in 5 decimal, that's all we can bring it down to. All right, so now we are done and we have completed our modeling function right here. Q of t as a continuous decay model over here, continuous decay model. I'm looking at 200 initially times e to the minus 0.0231 t. That completes our function. That completes our function that models the amount of cesium-137 in t years, in some t years. So we've learned as a little experience right here. In this problem, I introduced for you that term where a lot, and actually not only a lot, all of the scientists and the mathematicians out there are using the term the half-life right here. Okay, so what did we see right here? So somewhere here and there in your textbooks, some textbook author will bring in the following 2 formulas. But don't get my intention incorrectly here. I don't really intend to put this as your formal learning. I'm just putting these formulas here for you to be aware that somewhere here and there some textbook will include these 2 formulas right here. But really, it's the more I make it as your formal learning, then it's just gonna make anyone learning the lesson more worry about there are too many formulas to remember. So here it's just to raise your awareness that there will be these formulas. Okay, so we have learned that. So half-life in the definition earlier, it was the time it takes to decay down to the half of the amount that was initially present. Okay, so now notationally, half-life is notated by the symbol 1/2 here, and it's quite a standard symbol using worldwide. Okay, being used worldwide. So half-life, the amount of time that the population decays to half of it is t1/2. And then so in quite a few textbooks out there, you may see the following formula being included in there: natural log of 2, and indeed negative natural log of 2 divided by k, like that, minus natural log of 2. And then apparently speaking, this formula is only in the problem where your process is a decay process. It's an exponential decay process. So you only see this formula anytime we're talking about exponential decay. Because in exponential decay, we're losing quantity over time like that. Okay, and then as we lose over time, there will be a certain time long enough where it hits to only half, and that's how we calculate the half-life there. And then so right from that version, it's just a different arrangement of the same relationship, actually, the same relationship, but now from that relationship we can rearrange t and k here, t1/2 and k here, into a different form. So k equals negative natural log of 2 and divided by the half-life right here. So this formula can be particularly useful Okay, for anyone who's willing to learn it right from this video. But like I said, I don't really intend to make anyone memorize these two formulas here. If you know it, that's good for you. If you don't, this is not a must. Okay, so now this formula here will be the one way to quickly solve for your k value, your relative rate or continuous rates. Once you have known half-life, once you have known how long it takes to decay a population down to only half of what initially present. All right. All right, so now after example 8, let's head into example 9, another situation to be introduced. And so at this point, I still want to particularly focus on your skill, how you can write your own modeling function, because that's the top priority. Take my words on that. In my working experience with these exponential growth or decay problem, no matter how the problem is given to you right there, top priority is being able to being able to write your own function. Okay, and so in that way, I'm trying to put you, the viewers, the learners, the students of mine, into as many situations as possible, so that you can identify and route your way. And once you can successfully write your own modeling function, whether it's a decay function, a decay model, or a growth model, okay, you can get the rest of the problem done smoothly. Okay, and so now let's look at example 9. We're still going to learn to read the description and write another modeling function. Okay. So now here we go at the wording description for example 9 right here. So the use of a new social networking website has been growing exponentially. So this is some proven fact maybe. Okay, but now it's indicating with that word right here, growing. And so the wording here is making it a little bit into some expectation for us. The problem will be an exponential growth according to this wording right here. But having this term or not is not important. Okay, so use of a new social networking website has been growing exponentially, with the number of new users doubling every 5 months. Okay, and now that's the end of one sentence, and then one more sentence that comes as the description right here. If the site currently has 120,000 users currently, so this is one time point right here. This is one time point currently. It has 120,000 users, but then it doubles every 5 months. Okay, so now if it think about it right now, if time 0, 5 months later, and the time here is in months right here, clearly. So in 5 months later, it's going to be 240,000. Okay, and in another 5 months there, okay, that means 10 months from this current time, then that means we're going to have 480,000 users, etc., etc. And that's the idea right there. So this key right here reveals some rate of the growing right here, some rates for growing. However, it's not clearly, in the end, it's still not the kind of rates where it grows by how much. Is that a 1% per year? Is that a 2% per year? It's not that kind of rate. It's not that kind of directly written out rates. Okay, so we're still going to have to read and understand a little more to find out what rates we're looking at. What precisely is the rate we're looking at. Okay, so now back on the wording description. So if the site currently has 120,000 users, right, and then we want to, and this trend continues, we want to write a function that models the number of users after t months. So after t months from this current point, you got to understand that after t months, it means from this current point. So from that information, now we have a lot to write down right here. Yes, we can call again the amount of users, the quantity of users, Q of t. Now this is about the number of users. I mean, this social networking website can be simply Facebook, okay, or TikTok, okay, or whatever the social networking platforms out there. There are a lot in these days out there. Okay, and this problem kind of describes a situation that, surprisingly how much and how quickly they grasp users' attention. Okay, and so this is not only for the scientists to learn, but this is for anyone doing business to also learn. The CEO of these companies, they want to know this information to see how fast their website that they constructed can grab their attention so that they can build their business better and better. And that's the idea. All right. So now, Q of T is the number of users. So now what I'm looking at now is that you see the statement that I highlighted earlier. Currently, the website currently has 120,000 users. That's it. And I mentioned earlier, so the current, it's a time point. All I see it's a time point. And then the problem wants us to write the model function here, the function here to model the quantity in some t months later, in some t months after that time point. So it's completely legal for us to use that time point currently, right there, that current time point to be our initial time. So that means now I'm looking at Q of 0 equals 120,000. Q of 0 equals 120,000. Okay, and then in that way, yes, this is Q sub 0 equals 120,000. That's what it is. All right, and then now it says the number of users doubles every 5 months. Double every 5 months. Okay, double every 5 months. So now, ladies and gentlemen, at some point in your learning, you will learn about these terms. Now, also this problem is a good place to bring it out. Okay, I don't need anyone to memorize because again, the lesson here is only use these terms once or twice maybe. Okay, or even the halftime term that I introduced earlier. But then I believe in my teaching philosophy, the more you see these problems in your actual applications out there, the more you see these terms in your applications out there, you will have it stay. But now here I formally give what it means by a double time here. Well, clearly this problem and the way the wording is indicating it doubles every 5 months. So that means the population here, the quantity here is growing. The number of users is growing. I mean, that's how that's how CEO of those website companies they want to look for. They want to look for the number of users to grow. The more exponentially it is, the better for their business. That's the idea right there. Okay, so now double time. What does double time mean? Similar to half time. So double time means the time. Okay, it's the time, it's the amount of time. Double time is the time it takes. Okay, the time it takes to double. All right, to double an amount or an initial amount. All right, so that gets things clear. An initial amount or an initial population. So when population grows like that, yes, there's a certain amount of time where it's going to get double. We call that, it's double time. Say, the initial amount, the initial population in Utopia is 25 million in 2000, and it's going to double to become 5 million in 20 years, for example. Then 20 years is called the double time for utopian population. So that's just a scenario right there. And so now, generally speaking, double time is the time it takes to double an initial amount. To double an initial amount. All right, so that's what it is. That's what it is. And so now, I have to sadly erase this, but of course it gives us a clear key that our population here, our number of users here is growing, and I have made it this clear earlier. All right. So right from that information, the wording says it doubles every 5 months. Double every 5 months. And then we already consider that this is when time t equals 0. This t equals 0, it's 120,000 users for that website. So that means, according to the information given, the number of users, this Q right here, this quantity doubles every 5 months. So that means we extracting from that information, we come to the following understanding. Q of 5, because T is in time, in months, okay? T is in month. Okay, T is in months. Okay, so Q of 5, so this is 5 months. In 5 months, we're looking at 240,000 users. It doubles. The population doubles right there. All right, and so now we have enough information. And again, I see this process as a continuous growing process right there, and allow me to stick with the model where a much bigger majority of mathematicians and scientists out there are using the base E model, the continuous growth model. This is a growth problem right here, an exponential growth problem. The wording was indicating it's growing exponentially. Okay, all right. So now for an exponential growth and for a continuous growth model, I'm going to go as far as a general formula: Q sub 0 times e to the kt, and this is our relative rate. Okay, and so after doing as many problems as possible, you will start getting into a routine right here. So now we already knew that we had this quantity. Okay, there are so many different ways to explain, but in the end, this quantity here can be used as our initial amount. So now Q of t must be 120,000 times e to the kt. All right, and so now we've had this formula halfway done. So now the next part here, just like the earlier problem, I'm going to make use of this information. At some other time point here, our population, our quantity reaches to a different value, And I hope at this point, since example 6 until now, 4 problems so far, you can already see that it's all about this kind of idea right here. We don't have a rate clearly indicated, but at least we have, aside from the initial amount right there, which is happening at time e equals 0, we're going to have an amount. We generally have an amount given at a different time point, a time point other than time 0. And then from that, we use that as the information to solve for our we solve for our relative rate or continuous rate. And that's the generality out there. And so now when t equals 5, my right-hand side becomes 120,000 times e to the 5t, and I mean 5k. All right, and then on the left-hand side, we're looking at 240,000 to equal this setup right here. So now we have come to our exponential equation. Okay, so now after seeing this as an exponential equation, I'm going to go ahead and divide both sides by 120,000 right here. So we're looking at e to the 5k equals to 240,000. Okay, and allow me to start speeding up the steps here a little bit, because I'm assuming that students are all fluent at this point, and to expect that we're canceling both sides here by 120,000. And so that now in my next step here, I'm looking at 240 over 120. Okay. And so now reducing my equation a little further, I'm just saying reducing my equation in a sense of working a little further on the right-hand side here. Then I have e to the 5k equals 2. E to the 5k equals 2. All right, so now looking at this equation, what we're having here is an equation in exponential form. All right, so now again, that means 5k in the equivalent logarithmic form right here. 5k will equals log base e or natural log of 2. Okay, 5k over 5k equals natural log of 2 right there. All right, and so now k will equals 1/5 natural log of 2. 1/5 natural log of 2. Right there. All right, so it's natural log of 2 and divided by 5 right there. Okay, and that's our the rate right there. Okay. All right, so at this point right here, Now we're looking at, well, I have already expressed k equals a 1/5 natural log of 2. So I can just simply hop over to my calculator screen, right, to get a decimal value of this expression, and then we're gonna, and then we're ready to complete our the exponential function right there, our continuous growth model. All right. All right, so here we go. We have 1/5 times natural log of 2 this time. All right. And that is our answer over here. It's being positive 0.138629 and a lot longer. Positive 0.138629 and a lot longer. And so in this lecture, I am going to go with 5 decimal places. All right, so that means k is approximately 0.13863 in 5 decimal places. And it's a positive value this time. The population is growing. All right, so in that way, now I'm seeing my complete continuous exponential model to be 120,000 times e to the 0.13863 t. All right, and that is how it's done. All right. All right, and so now we are ready for another example over here. And let's call that example 10 for this lecture over here. Okay, so again, I'm going to swing over to the computer station and bring the worded description of the problem on screen right there. All right. All right, so the count of bacteria in a culture was 800 after 10 minutes and 1800 after 40 minutes. Find a function that models the bacteria count in the culture as at t minutes. Okay. The count of bacteria in a culture was 800 after 10 minutes. All right. So this wording indeed is indicating that it's not quite our initial value, but we do know some quantity at some 10 minutes after the initial amount. And then we know another quantity after some further time. All right, and that's all we have for this information. And then we are asked to find a function that models the bacteria count or model the quantity in some t minutes later. So the default time period here is in minutes, okay, is in each minute right there. But really, that is all we have. That is all we have. We don't even know the initial amount here at this point. So here's how I'm seeing it. We can call Q of t, yes, just like the earlier problem right there, the population of bacteria or the quantity of bacteria here. Okay, this is a population, okay, or how about the count? The bacteria count, okay, in t minutes. All right. But see, the reason I was saying that we did not really know, and the problem did not give us the initial time, because right at the beginning, all it says the count of bacteria was already 800 after 10 minutes. So that means it's whatever initial amount that is, but it already grew to 800 in 10 minutes. That's all we know. So really, do we know Q of 0 this time? We don't know. We don't know that information. But on the other hand, we actually know Q of 10. The count grew to 800 after 10 minutes. So whatever starting amount right there, but by 10 minutes later, it grew to 800. So we have this information. We can write it down. We can note it down right there. All right. And further, we knew for another additional, so So 1800 after 40 minutes, 1800 after 40 minutes, that means that 40 minutes right there is t equals 40 minutes. 40 minutes after the initial amount. We don't know the initial amount, but 40 minutes later, it grew to 1800. So that means Q40. So that means this is also, you can think of that as another 30 minutes away, another 30 minutes after this time point right here. Okay, but now this is equal 1800. Okay, Q of 10 equals 800. Q of 40 equals 1800. All right, so now we want to find the function that models this according to this description right here. And also, we don't know the k, we don't know the rate right here. So we're going to have to only rely on this given information. Yes, I will stick with the continuous growth model again. We know it's growing because look at the two values, the two quantity at the two time points right here. At some later time, we got a higher count. So clearly it's a growth. No need to argue about that, right? No doubt about that. So now here's how I'm seeing it with the unknown time right here. Let's look for, how about we're going to go ahead and set up our function first. Q of t has to be q sub 0 times e to the kt. All right. Q of t equals q sub 0 times e to the kt. Okay, so now from what I know right here, from what we have already know right here, Q of 10 equals 800. So that means on one hand we produce one equation. 800 equals whatever for Q0 we didn't know, times e to the 10k. All right, e to the 10k. And then on another hand, we know that when t equals 40, our value there is 1800. So we're having 1800 equals q sub 0 times e to the 40k, because I substituted 40 for t. Here I substituted 10 for t. We've produced two equations, but they're both related to q sub 0, the same q sub 0 and the same k value in both equations. Yeah. All right, the same q sub 0 and the same k right there. All right, so now in that way I can see the following. Now still it's the same q value. So I'm gonna on this equation, let's separate it out into two separate spaces right here. On this equation, I'm gonna think about q sub 0 can equal 800 divided by e to the 10k. I divided both sides. So let me write it down a little further down so that I can explain some of the steps. Q of sub 0 can be obtained by dividing both sides by e to the 10k. Okay, and that's how I consequently got that. See, I divided e by the 10k, e to the 10k, because it's a product here. So that's how I ended up with q. From this equation, I ended up with q sub 0 equals 800 over 10k. The same equation I'm going to handle the same way right here. I'm going to divide both sides by e to the 40k. Okay, and the way I'm doing here is not the only way. Indeed, there are faster solutions as well, but I'm showing the solution that's the easiest to understand for a lot of students and people right there. All right, so now that means we're looking at here, after dividing e to the 40k from both sides, then I'm going to end up with another. So q sub 0 equal 1800 divided by e to the 40k. So q on one hand equals this expression, and the same q on the other hand equals to the other expression right here. So now on my next board, allow me to bring up the following relationship. I now see that we have 800 over e to the 10k. It's already equal to q sub 0. But q sub 0, on the other hand, as I said, equals to 1800 over e to the 40k. And so now in that way right here, these two have to be equal to each other. These two have to be equal from each other. Okay? All right, so now we can take the reciprocal of this equation, take the reciprocal side by side to this equation. So that means on the left-hand side, I'm looking at e to the 10k can over 800 can equal e to the 40k over 1,800 or 1,800. Okay, and we keep getting closer and closer. So now I want everyone to see that I can multiply both sides by that 800. Some more algebra steps right here. So now on the left-hand side, I'm going to have e to the 10k equals 2, and then I have 800 over 1,800, okay, times e to the 40k. So this is after I multiply the 800 to the other side and isolate out that fraction 800 over 1,800. Yeah. And then yes, we have some cancellation here, and 18 cancel with 8 into a common factor of 2, so it's going to be a 4/9 altogether. So 800 over 1,800 here in the next step, we're looking at a 4/9 e to the 40k equals e to the 10k on the left-hand side. Now we're getting a lot closer. All right, so now with this equation, ladies and gentlemen, it's another exponential equation that we have seen back in our time learning about how to solve, back in our lecture where I show how to solve exponential equations. We have two different exponential terms right here. Okay, but good news, they're all with the same base right here. So the one standard technique right here, we're going to take a logarithm both sides. And again, this is about that 20% on each problem where we have to use a logarithm. Okay, 20% on each problem where we apply exponential functions. We have to use a logarithm. Okay, so now left-hand side, I'm going to take a logarithm, and see, it's base e and base e, so it's best to use a natural log. It's just a choice of the log, but it's a lot of time it's best to use a natural log, and particularly here it's already base e. All right, so natural log of the of the e to the 10k, and I will take natural log of the 4/9 times e to the 40k. I'm taking the natural log both sides equally. And so now in that way, left-hand side with the property of log now at this point. So here, see, we're treating log as a tool that we use, but that's how we apply logarithm. Okay, so now with the property of logarithm, we have already learned that we can write this as a 10k, okay, times and see, log base e of e to some power, so that log cancel with e, that's why I only end up with 10k. All right, right-hand side, I have a product. So that means I have a logarithm of 4/9 as one quantity in that product, plus logarithm natural log of e to the 40k. Okay, and then in my next step, 10k equals a natural log of 4/9 plus, and then this here I can do the similar thing as I did earlier here. So that I bring this down to according to the logarithm property right here, it becomes a 40k. All right, 40k there. All right, so now I can bring all the k terms to one side. So now I'm looking at this, and so I'm subtracting 40k from both sides. Okay, subtracting 40k from both sides, and that gets me minus 30k equals a natural log of 4/9. All right, so that gives me k equals negative 1/30 times natural log of 4/9. And this now is ready for us, ready to provide for us a value for k right there. All right, so now I'm going to take this value, okay, and punch it in the calculator. I'm going to type this expression in the calculator and get an actual value for that. All right, so now on my calculator, -1 1/30 times natural log of 4/9. All right, and that gives me this positive k. So let's check for consistency right here. The problem was a growth, okay? It was a natural growth problem, like an exponential growth problem. So it makes perfect sense and consistent with the fact that this k has to be a positive value. Okay, so now I'm going to return to the board. And so what I have here is, and in that 5 decimal places, I'm going to go with about 0.02703. All right, 0.02703. 0.02703. So now with this, I'm going to head back to the other board and erase some work that we have done earlier. All right, so now at this point, I have found my k value. So now my function is further completed, but not completely done. So I have q of t equals some q sub 0 initial point, initial time, okay, times e to the 0.02703 t. Now we have that value. All right, and so now we can just find our way to solve for q sub 0 over here. And as a matter of fact, anyone can think about substituting the 10 here into t and 800 into that. Yes, that's the way, but we actually already had this. If you recall earlier to the part that I already erased right there, one of the two equations, q sub 0 equals 800 divided by the 800 divided by e to the 10k. This is the one right there. Okay, so we can just directly plug our found value for k in here, and that will be our q sub 0. Because if we were going with the solution that I was saying earlier, we're going to end up with this anyway. So yes, that will be the way, but we already had some work done that I had to erase, so I'm going to just bring that back a little bit and put it in. Okay, so now, well, back to this equation. If we think about substituting in that pair of values, 10, 800 or 40, 1800, they're both going to work. Okay, so we can think about 800 equals q sub 0 times e to the 0.02703 times 10. Yes, so that's one way, and then we solve for q sub 0. But solving that for that work is exactly the same as this step. And that's what I was trying to say right here. And so now it's 800 divided by e to the 10 times 0.02703. All right, and that's how that step led into this. All right, so now it's just a matter of heading over to the calculator and punch in a value for this. Okay, punch in this expression to get a value for that. Okay. So now on my calculator, 800, I'm dividing by e to the 0.02703. All right, so with this value right there, it's about our initial amount. All right, so I'll just round to the nearest whole value right here, because these are the actual bacteria count right there. All right. So now that means we have found it is about approximately about in nearest count right there, it's 779 bacteria. Okay, so that was the initial amount right there. So now I'm going to get to my other board and write down the complete equation. All right, so now our continuous growth model here is q of t equals 779 times e to the 0.02703 t. That is our function right there, our continuous growth model. All right.